Section: Contents. We're here to discuss the recent progress in large language models, LLMs. These models have shown that as they grow in size, even up to billions of parameters, the quality of language generation improves significantly. However, this growth comes with a downside. It increases the time it takes for the model to make inferences, which can be a problem in practical applications. From a systems perspective, the main issue causing this delay is the memory bandwidth of the accelerators, not the arithmetic computations. This is due to the sequential nature of autoregressive decoding, where each forward pass requires transferring the entire model parameters from high bandwidth memory, HBM, to the accelerator's cache. This process only generates a single token and doesn't fully utilize the computational potential of modern accelerators, leading to inefficiency. One way to speed up LLM inference is to increase the arithmetic intensity, the ratio of total floating point operations to total data movement, of the decoding process and reduce the number of decoding steps. Speculative decoding has been proposed as a solution. This method uses a smaller draft model to generate a sequence of tokens at each step, which is then refined by the original, larger model for acceptable continuation. However, finding a suitable draft model is challenging, and it becomes even more difficult when trying to integrate the draft model into a distributed system. In this paper, we propose a different approach. Instead of using a separate draft model, we suggest using multiple decoding heads on top of the backbone model to speed up inference. We introduce MEDUSA, a method that enhances LLM inference by integrating additional decoding heads capable of predicting multiple tokens at the same time. These heads are fine-tuned in a parameter-efficient manner and can be added to any existing model. MEDUSA doesn't require a new model, making it easy to integrate into current LLM systems, including those in distributed environments. We further improve MEDUSA with two key insights. First, the current approach of generating a single candidate continuation at each decoding step leads to a restricted acceptance length and inefficient use of computational resources. To address this, we propose generating multiple candidate continuations using the MEDUSA heads and verifying them concurrently through a simple adjustment to the attention mask. Second, we introduce a typical acceptance scheme that selects reasonable candidates from the MEDUSA head outputs. We use temperature as a threshold to manage deviation from the original model's predictions, providing an efficient alternative to the rejection sampling method. To equip LLMs with predictive MEDUSA heads, we propose two distinct fine-tuning procedures tailored to various scenarios. For situations with limited computational resources or when the objective is to incorporate MEDUSA into an existing model without affecting its performance, we recommend MEDUSA-1. This method requires minimal memory and can be further optimized with quantization techniques similar to those in QLORA, without compromising the generation quality due to the fixed backbone model. However, in MEDUSA-1, the full potential of the backbone model is not utilized. We can further fine-tune it to enhance the prediction accuracy of MEDUSA heads, which can directly lead to a greater speedup. Therefore, we introduce MEDUSA-2, which is suitable for scenarios with ample computational resources or for direct supervised fine-tuning, SFT, from a base model. We propose different strategies for obtaining the training datasets depending on the model's training recipe and dataset availability. When the model is fine-tuned on a public dataset, it can be directly used for MEDUSA. If the dataset is unavailable or the model underwent a reinforcement learning with human feedback (RLHF) process, we suggest a self-distillation approach to generate a training dataset for the MEDUSA heads. Our experiments primarily focus on scenarios with a batch size of 1, which is representative of the use case where LLMs are locally hosted for personal use. We test MEDUSA on models of varying sizes and training settings, including Vicuña 7b, 13b, trained with a public dataset, Vicuña 33b, trained with a private dataset, and Zephyr 7b, trained with both supervised fine-tuning and alignment. MEDUSA can achieve a speedup of 2.3 to 3.6 times across different prompt types without compromising on the quality of generation. Section Summary. Large language models, LLMs, have shown improved language generation with larger model sizes, but this leads to increased inference latency due to memory bandwidth limitations. To address this, we propose MEDUSA, a method that integrates additional decoding heads into the backbone model to concurrently predict multiple tokens, resulting in faster inference without the need for a new model. We enhance MEDUSA by generating multiple candidate continuations and using a temperature-based threshold for efficient acceptance, achieving a speedup of 2.3 to 3.6 times without compromising generation quality. Section: LLM Inference Acceleration. We're going to discuss how to speed up the inference process of large language models, LLMs. The main issue with LLMs is that they are memory-bound due to the auto-regressive decoding process. There have been several solutions proposed to address this, with the aim of improving the speed and efficiency of the process. One common method has been batch inference, which increases the intensity of the calculations and helps to overcome memory limitations. However, with LLMs, the model parameters and the key value, KV, cache take up a lot of memory, which makes it difficult to use large batch sizes. There are two main strategies to address this: reducing memory usage to allow for larger batch sizes, and reducing the number of decoding steps to directly decrease latency. One way to reduce the KV cache is to use methods like multi-query attention and grouped query attention. These methods use fewer key and value heads in the attention modules compared to query heads, which significantly reduces the memory usage of the KV cache. This allows for larger batch sizes and better use of the accelerator. There are also proposals to only keep the most important KV tokens, which further reduces the KV cache. Quantization techniques are another way to reduce memory usage. These techniques rescale between activations and parameters to remove outliers and simplify the quantization process. They also break down matrix multiplications into mostly 8-bit and some 16-bit operations. Other methods round weight columns into 3/4 of a bit, or use an activation-aware quantization scheme to protect important weights and compress LLMs to 3/4 of a bit. Speculative decoding is another approach that aims to reduce the total number of decoding steps by executing several steps in parallel. This is done by using a smaller draft model to guess several subsequent words, which the LLMs then collectively evaluate and accept if appropriate. We propose using the original model to make predictions instead of introducing an additional draft model. This is simpler and integrates more easily into existing systems. The way text is sampled from LLMs can greatly affect the quality of the output. Direct sampling can sometimes lead to incoherent or nonsensical results. To address this, truncation sampling schemes have been introduced. These methods aim to produce high-quality and diverse samples by performing sampling on a truncated distribution over a specific allowed set at each decoding step. Different strategies define this allowed set in different ways. For example, top K sampling keeps the K most likely words, while top P sampling includes the smallest set of words that account for P% of the probability. Our method, called MEDUSA, follows the same framework as speculative decoding. Each decoding step consists of 3 substeps: generating candidates, processing candidates, and accepting candidates. For MEDUSA, the first step is done by MEDUSA heads, the second step is done by tree attention, and the third step can be done by either rejection sampling or typical acceptance. We also propose 2 extensions to MEDUSA, including self-distillation and typical acceptance, to handle situations where no training data is available for MEDUSA and to improve the efficiency of the decoding process, respectively. Section Summary. LLM inference inefficiency is primarily due to the memory-bound nature of auto-regressive decoding. Existing methods to address this issue include reducing memory consumption, minimizing decoding steps, quantization techniques, and speculative decoding. Truncation sampling schemes have also been introduced to improve the quality of generated output from LLMs. MEDUSA, a framework that follows speculative decoding, consists of generating candidates, processing candidates, and accepting candidates, and can be fine-tuned and extended for different use cases. Section: MEDUSA heads. We're introducing a concept called MEDUSA heads, which is a method to improve the efficiency of speculative decoding. Speculative decoding is a process where we try to predict future tokens using a smaller, auxiliary model. The challenge here is to create a model that's small enough to be efficient, but also effective enough to generate predictions that the main model will accept. Existing methods often involve pre-training a smaller model separately, which can be computationally expensive. For instance, one study reported using 275 hours on an NVIDIA A100 GPU. This separate pre-training can also cause a shift in the distribution between the smaller model and the main model, which can lead to predictions that the main model doesn't favor. To address these issues, we've developed MEDUSA heads. These are additional decoding heads that we attach to the last hidden states of the main model. For each position in the sequence, we add multiple decoding heads. Each head is used to predict a token in a future position. The prediction from each head is represented as a distribution over the vocabulary. We use a simple feed-forward network with a residual connection for each head. This design has proven to be effective. The weights of the network are initialized in a way that aligns the initial predictions of the MEDUSA heads with those of the main model. Unlike the smaller model used in speculative decoding, MEDUSA heads are trained alongside the main model. This allows us to fine-tune large models even on a single GPU, and ensures that the distribution of the MEDUSA heads aligns with that of the main model. This approach also doesn't add complexity to the system design and is suitable for distributed settings. With MEDUSA heads, we can generate probability predictions for multiple future tokens. These predictions allow us to create multiple continuations as candidates. While previous studies suggest sampling a single continuation as the candidate, using multiple candidates can improve the expected acceptance length within a decoding step. However, more candidates can also increase computational demands. To balance this, we use a tree-structured attention mechanism to process multiple candidates at the same time. This attention mechanism differs from the traditional causal attention paradigm. In this framework, only tokens from the same continuation are considered as historical data. We incorporate the tree structure into our attention mask, which allows us to process multiple candidates simultaneously without the need to increase the batch size. The number of new tokens is calculated as the product of the number of top predictions from each head. While we've demonstrated a simple way to construct the tree structure, it's possible to construct it in a more sophisticated way and take advantage of the varying accuracy of different top predictions from different heads. We'll discuss this in a later section. Section Summary. The authors introduce MEDUSA heads, which are additional decoding heads appended to the last hidden states of the original model. These heads are trained in conjunction with the original model, mitigating the distribution shift problem and allowing for fine-tuning of large models even on a single GPU. They also propose a tree-structured attention mechanism to process multiple candidates concurrently, enhancing the expected acceptance length within a decoding step. This attention mechanism incorporates a tree structure into the attention mask, enabling the processing of numerous candidates simultaneously without the need to expand the batch size. Section Training Strategies. We'll start by discussing the training strategies for the MEDUSA heads, a key component of our model. At the most basic level, we can train these heads by keeping the backbone model constant and focusing only on the MEDUSA heads. This method is simple and doesn't require a lot of computational power. However, if we train the backbone model alongside the MEDUSA heads, we can significantly improve the accuracy of the MEDUSA heads. Depending on the computational resources available and the specific needs of the use case, we suggest two levels of training strategies for the MEDUSA heads. For this discussion, we're assuming that we have a training dataset that matches the output distribution of the target model. This could be the dataset used for supervised fine-tuning, SFT, of the target model. We'll talk about how to get rid of the need for such a dataset using a self-distillation approach later on. The first strategy, which we'll call MEDUSA 1, involves freezing the backbone model. To train the MEDUSA heads with a frozen backbone model, we use the cross-entropy loss between the prediction of the MEDUSA heads and the actual result. Specifically, given the actual token at a certain position, the loss for a particular head is calculated as the negative logarithm of the probability of the actual token predicted by that head. We've noticed that this loss is larger when the head number is larger, which makes sense since the prediction of a head is more uncertain when the head number is larger. To balance the loss of different heads, we can add a weight to the loss of each head. The total MEDUSA loss is then the sum of the weighted losses of all heads. In practice, we set the weight as a constant like 0.8 raised to the power of the head number. Since we only use the backbone model for providing the hidden states, we can use a simplified version of the backbone model to reduce the memory usage. This makes it possible to speed up LLM inference in a more accessible way. As with this simplification, MEDUSA can be trained for a large model on a single consumer GPU similar to QLORA. The training only takes a few hours, for example, 5 hours for MEDUSA 1 on Vicuña 7B model with a single NVIDIA A100 PCIe GPU to train on 60K shared GPT samples. The second strategy, which we'll call MEDUSA 2, involves joint training. To further improve the accuracy of the MEDUSA heads, we can train them together with the backbone model. However, this requires a special training recipe to maintain the backbone model's next token prediction capability and output quality. To achieve this, we propose 3 strategies. 1. Combined loss. To maintain the backbone model's next token prediction capability, we need to add the cross-entropy loss of the backbone model to the MEDUSA loss. We also add a weight to balance the loss of the backbone model and the MEDUSA heads. Therefore, the total loss is the sum of the backbone model's loss and the weighted MEDUSA loss. 2. Differential learning rates. Since the backbone model is already well trained and the MEDUSA heads need more training, we can use separate learning rates for them to enable faster convergence of MEDUSA heads while preserving the backbone model's capability. 3. Heads warm-up. We've noticed that at the beginning of training, the MEDUSA heads have a large loss, which leads to a large gradient and may distort the backbone model's parameters. To address this, we can use a 2-stage training process. In the first stage, we only train the backbone model as in MEDUSA 1. In the second stage, we train the backbone model and MEDUSA heads together with a warm-up strategy. Specifically, we first train the backbone model for a few epochs, then train the MEDUSA heads together with the backbone model. Besides this simple strategy, we can also use a more sophisticated warm-up strategy by gradually increasing the weight of the backbone model's loss. We find both strategies work well in practice. By combining these strategies, we can train the MEDUSA heads together with the backbone model without compromising the backbone model's capability. Moreover, this recipe can be applied together with supervised fine-tuning, SFT, enabling us to get a model with native MEDUSA support. Section summary. In training MEDUSA heads, we can either freeze the backbone model and focus solely on the heads, which requires minimal computational resources, or train the backbone model along with the heads to enhance accuracy. For the frozen backbone approach, we use cross-entropy loss between the heads' predictions and the ground truth, with a weight assigned to balance the loss of different heads. In joint training, we add the backbone model's cross-entropy loss to the MEDUSA loss, use separate learning rates for the backbone and heads, and employ a warm-up strategy to prevent distortion of the backbone model's parameters. These strategies enable training MEDUSA heads without compromising the backbone model's capability. Section. Typical acceptance. In the realm of speculative decoding, researchers often use a method called rejection sampling to generate diverse outputs that match the original model's distribution. However, this method has been found to be less efficient as the sampling temperature increases. To understand this, imagine a scenario where the draft model is identical to the original one. In this case, if we use a method called greedy decoding, all outputs from the draft model will be accepted, maximizing efficiency. On the other hand, rejection sampling introduces extra overhead because the draft and original models are sampled separately. Even if their distributions align perfectly, the draft model's output might still be rejected. In real-world applications, we often use language model sampling to generate diverse responses, and the temperature parameter is used to adjust the creativity of the response. Therefore, higher temperatures should provide more chances for the original model to accept the draft model's output. We believe that it's not always necessary to match the original model's distribution. Instead, we suggest using a method we call typical acceptance to select likely candidates, rather than using rejection sampling. This method is inspired by truncation sampling studies. Our goal is to choose candidates that are typical, meaning they are not highly unlikely to be produced by the original model. We use the prediction probability from the original model as a measure for this and set a threshold based on the prediction distribution to determine acceptance. Specifically, when evaluating a candidate sequence made up of top predictions from the original language model and MEDUSA heads, we consider a condition that involves comparing the prediction probability of a token in the sequence to a threshold that depends on the entropy of the prediction distribution and two hyperparameters. This criterion is based on two observations. 1. Tokens with relatively high probability are meaningful, and 2. When the distribution's entropy is high, various continuations may be considered reasonable. During decoding, every candidate is evaluated using this criterion, and a prefix of the candidate is accepted if it meets the condition. To ensure that at least one token is generated at each step, we use greedy decoding for the first token and unconditionally accept it, while using typical acceptance for subsequent tokens. The final prediction for the current step is determined by the longest accepted prefix among all candidates. This method offers several insights. First, when the temperature is set to 0, it reverts to greedy decoding, as only the most probable token has non-zero probability. As the temperature surpasses 0, the result of greedy decoding will consistently be accepted with appropriate hyperparameters, since those tokens have the maximum probability, leading to maximum speedup. Similarly, in general scenarios, a higher temperature will result in longer accepted sequences, as confirmed by our experimental findings. In some cases, we assume the existence of a training dataset that matches the target model's output distribution. However, this is not always the case. For instance, the model owners may only release the model without the training data, or the model may have undergone a reinforcement learning with human feedback (RLHF) procedure, which alters the model's output distribution from the training dataset. To address this issue, we propose an automated self-distillation pipeline to use the model itself to generate the training dataset for MEDUSA heads, which matches the model's output distribution. The dataset generation process is simple. We first take a public seed dataset from a domain similar to the target model. Then, we use the prompts from the dataset and ask the model to respond to them. To obtain multi-turn conversation samples, we can sequentially feed the prompts from the seed dataset to the model. For models trained on both roles of the conversation, they can self-talk, and we can simply feed the first prompt and let the model generate multiple rounds of conversation. For MEDUSA 1, this dataset is sufficient for training MEDUSA heads. However, for MEDUSA 2, we find that solely using this dataset for training the backbone and MEDUSA heads usually leads to lower generation quality. This suggests that we also need to use the original model's probability prediction instead of using the ground truth token as the label for the backbone model, similar to classic knowledge distillation works. The loss for the backbone model is calculated by comparing the probability distribution of the original model's prediction at a certain position to the corresponding distribution of the backbone model. However, to obtain the original model's probability prediction, we need to maintain two models during training, which increases the memory requirements. To mitigate this issue, we propose a simple yet effective way to exploit the self-distillation setup. We can use a parameter-efficient adapter like LoRa for fine-tuning the backbone model. In this way, the original model is simply the model with the adapter turned off. Therefore, the distillation does not require additional memory consumption. Together, this self-distillation pipeline can be used to train MEDUSA 2 without hurting the backbone model's capability and introduce almost no additional memory consumption. Lastly, one tip about using self-distillation is that it is preferable to use LoRa without quantization in this case. Otherwise, the teacher model will be the quantized model, which may lead to lower generation quality. Section summary. In speculative decoding, rejection sampling can result in decreased efficiency as the sampling temperature increases. To address this, we propose a typical acceptance scheme that selects plausible candidates based on the prediction probability from the original model, ensuring that the generated tokens are meaningful and diverse. Additionally, we introduce a self-distillation pipeline to generate a training dataset for MEDUSA heads that matches the output distribution of the model, using prompts from a seed dataset and the model's own responses. This pipeline can be used to train MEDUSA 2 without compromising the backbone model's capability and with minimal additional memory consumption. Section. Searching for the optimized tree construction. We're going to discuss how we can optimize the construction of a tree structure. The simplest way to do this is by using the Cartesian product, but this might not always be the best choice if we have a fixed number of total nodes in the tree. Here's why. The accuracy of candidates made up of the top predictions from different heads can vary. So, we can use an estimate of this accuracy to help us build the tree. We can do this by using a calibration dataset and calculating the accuracies of the top predictions from different heads. Let's say we denote the accuracy of the ith top prediction of the kth head as A_k I. If we assume the accuracies are independent, we can estimate the accuracy of a candidate sequence made up of the top predictions from different heads as the product of A_j, I_j, for j from 1 to k. We can denote the set of all possible combinations of these top predictions as I, and each element of I can be mapped to a node of the tree. This includes not just leaf nodes, but all nodes. The expected length of a candidate sequence can then be calculated as the sum of the product of A_j, I_j, for all combinations in I. When we build a tree by adding nodes one by one, the contribution of a new node to the expectation is exactly the accuracy associated with the node. So, we can add nodes to the tree by choosing the node that is connected to the current tree and has the highest accuracy. We can repeat this process until we reach the desired number of nodes. This way, we can build a tree structure that maximizes the expected acceptance length. An example of this is the sparsely constructed tree for the MEDUSA 2 Vicuña 7b model, which extends 4 levels deep. This tree was initially formed through a Cartesian product approach and then refined by pruning based on the statistical expectations of the top k predictions from each MEDUSA head measured on the alpaca eval dataset. Next, we'll present 2 sets of experiments to demonstrate the effectiveness of MEDUSA under different settings. First, we'll evaluate MEDUSA on the Vicuña 7b and 13b models. Second, we'll evaluate MEDUSA on the Vicuña 33b and Zephyr 7b models to study the effectiveness of self-distillation. We'll use 3 terms throughout these experiments. 1. Acceleration rate. This is the average number of tokens decoded per decoding step. In a standard auto-regressive model, this rate is 1.0. 2. Overhead. This is used to characterize the per decoding step overhead compared to classic decoding. It's calculated by dividing the average per step latency of the MEDUSA models by that of the vanilla model. 3. Speedup. This refers to the wall time acceleration rate. For all the experiments, we'll use the axolotl framework for training. We'll train 5 MEDUSA heads with 1 layer and set the learning rate of MEDUSA heads to be 4 times larger than the backbone model. We'll use the Vicuña model class, which includes chat models of varying sizes that are fine-tuned from the llama model. We'll use the shared GPT dataset to train the MEDUSA heads on the 7b and 13b models for 2 epochs. We'll use a global batch size of 64 and a peak learning rate of 5e4 for the backbone and 2e3 for MEDUSA heads and warm up for 40 steps. We'll first train the models with MEDUSA 1 and use these trained models as initialization to train MEDUSA 2. Section summary. The section discusses the construction of an optimized tree structure for the MEDUSA model. By estimating the accuracy of candidate sequences composed of top predictions from different heads, a tree structure can be constructed that maximizes the expectation of the acceptance length. The process involves greedily adding nodes to the tree based on their connection to the current tree and their accuracy. Additionally, the section mentions the experimental setup and evaluation of MEDUSA under different settings, including the performance of MEDUSA 1 and MEDUSA 2 on different models and the effectiveness of self-distillation. Section: Results. We've gathered our findings and presented them in a figure. We used the basic Hugging Face model as our starting point. From the figure, it's clear that for the 7 billion parameter models, the MEDUSA 1 and MEDUSA 2 configurations significantly boost processing speed, measured in tokens processed per second. MEDUSA 1 speeds up processing by a factor of 2.18, while MEDUSA 2 further improves this to a factor of 2.83. When we applied these configurations to the larger 13 billion parameter model, MEDUSA 1 increased speed by a factor of 2.33, while MEDUSA 2 maintained a similar speed boost of 2.83 times the baseline. We also charted the speed increase for each category using the MEDUSA 2 Vicuña 7B model. We found that the coding category saw a speed increase of 3.29 times, suggesting that MEDUSA is particularly effective for tasks in this area. This indicates a significant opportunity for optimizing coding language models, which are widely used in software development and other programming-related tasks. The extraction category showed the highest speed increase at 3.62 times, indicating that this task is highly optimized by MEDUSA. Overall, our results suggest that MEDUSA significantly enhances processing speed across different model sizes and tasks. In our experimental setup, we focused on cases where self-distillation is necessary. We used the Vicuña 33B model and the Zephyr 7B model as examples. Following the procedure we described earlier, we first generated datasets using some seed prompts. We used Shared GPT and UltraChat as the seed datasets and collected a dataset of about 100,000 samples for both cases. Interestingly, we found that the Zephyr model can continue to generate multiple rounds of conversation with a single prompt, which makes it easy to collect a large dataset. For Vicuña 33B, we generated multi-turn conversations by iteratively feeding the prompts from each multi-turn seed conversation. Both models were trained with a sequence length of 2048 and a batch size of 128. We used MEDUSA 2 for both models, and instead of using a two-stage training procedure, we gradually increased the value of theta_0 to its peak at the end of the training using a sign schedule, which we found to be equally effective. We set the peak learning rate of the backbone LoRa adapter to be 0.0001 and the warm-up steps to be 20. Since the self-distillation loss is relatively small, we set the lambda_0 in the equation to be 0.01. Our table complements these findings by comparing various MEDUSA 2 models in terms of their acceleration rate, overhead, and quality on MT-Bench. Notably, while the MEDUSA 2 Vicuña 33B model shows a lower acceleration rate, it maintains a comparable quality. We hypothesize that this is due to a mismatch between the hidden training dataset and the dataset we used for self-distillation. These results underscore the complex interplay between speed and performance when scaling up model sizes and applying self-distillation techniques. The findings also highlight the potential of the MEDUSA 2 configuration to boost efficiency in processing while carefully preserving the quality of the model's outputs, suggesting a promising direction for co-optimizing language models with MEDUSA heads. We conducted an ablation study of tree attention on the writing and roleplay categories from the MT-Bench dataset using MEDUSA 2 Vicuña 7B. We aim to illustrate tree attention's motivation and its performance. Our figure compares the acceleration rate of randomly sampled dense tree configurations against optimized sparse tree settings. The sparse tree configuration with 64 nodes shows a better acceleration rate than the dense tree settings with 256 nodes. The figure presents the speed for both dense and sparse tree settings. The trend observed here indicates a notable decrease in speed as the additional length increases. This suggests that while sparse tree attention is beneficial for maintaining a steady acceleration rate, it comes with the trade-off of reduced speed, particularly at higher additional lengths. The observed decline in speed is attributed to the increased overhead introduced by the hardware architecture. While a more complex tree can improve the acceleration rate, it does so at the cost of speed due to the hardware-imposed overhead. We studied the thresholds of typical acceptance on the writing and role-play categories from the MT Bench dataset using MEDUSA 2 Vicuña 7b. Using the Vicuña 7b model, we aligned our methodology with the approach delineated by setting the alpha equal to the square root of epsilon. Our figure presents a comparative analysis of our model's performance across various sampling settings. These settings range from a threshold epsilon starting at 0.01 and incrementally increasing to 0.25 in steps of 0.01. Our observations indicate a discernible trade-off. As epsilon increases, there is an elevation in quality at the expense of a reduced acceleration rate. Furthermore, for tasks demanding creativity, it is noted that the default random sampling surpasses greedy sampling in performance, and the proposed typical sampling is comparable with random sampling when epsilon increases. Section Summary. The results show that the MEDUSA 1 and MEDUSA 2 configurations lead to a significant increase in speed for the 7B and 13B models, with speedups ranging from 2.18 to 2.83 times. The coding and extraction categories benefit the most from MEDUSA, with speedups of 3.29 and 3.62 times, respectively, suggesting its effectiveness in optimizing coding language models. Additionally, the MEDUSA 2 Vicuña 33B model maintains comparable quality while showing a lower acceleration rate, indicating the complex interplay between speed and performance when scaling up models and applying self-distillation techniques. Section: Effectiveness of two-stage fine-tuning. We're going to delve into the effectiveness of a two-stage fine-tuning process. We've compared two different fine-tuning strategies for the Vicuña 7B model. One strategy involves directly fine-tuning the model with the MEDUSA heads, while the other, MEDUSA 2, involves a two-stage fine-tuning process. Our findings suggest that using MEDUSA 2 for fine-tuning not only maintains the quality of the model but also enhances its speed compared to the first strategy, MEDUSA 1. To wrap up our discussion, we've introduced MEDUSA, an innovative approach to speed up the inference process of large language models by adding extra predictive decoding heads. This allows the models to generate multiple tokens at each step, bypassing the slow process of sequential auto-regressive decoding. We've shown two methods, MEDUSA 1 and MEDUSA 2, that effectively train these additional heads without compromising the model's performance. Our experiments on various models and training methods consistently show a speed increase of 2.3 to 3.6 times during single prompt inference across different prompt types and models. MEDUSA's main strengths lie in its simplicity, efficient use of parameters, and easy integration into existing systems. By leveraging speculative decoding concepts, MEDUSA eliminates the need for specialized draft models. The standard acceptance scheme also simplifies the process by avoiding rejection sampling, while still producing reasonable outputs. Lastly, the fine-tuning processes ensure high-quality generations without negatively impacting the original model's performance. We'd like to express our deep appreciation to several individuals who made significant contributions to this project. Juehan Lee provided invaluable insights on large language model serving. We highly recommend checking out Johan's VLLM project, it's truly remarkable. Xiaoji Bai was instrumental in crucial discussions that helped shape the early stages of this work. Denny Zhou introduced the truncation sampling scheme to Tianl and encouraged him to delve into the area of large language model serving. Yanping Huang highlighted the memory-bound challenges associated with large language model serving to Tianl.